So, as I've already been introduced, my name is Erin Russell. This research was done with Dr. Michal Ganachik, and it's on inverse eigenvalue problems for special stochastic matrices. So if we go along, I'm just going to give a short introduction and describe what we're going to go through. So we're going to go through some preliminary tools first, and then we're going to go through graph construction, solving the IEP for circulates, which is the inverse eigenvalue problem, which I will define later, don't worry about that. And then doubly stochastic matrices, solving the SDIEP, which is the IEP specifically for symmetric doubly stochastic matrices. And then we're going to go through some very quick applications. Even though this is an applied mathematics talk, it's a little bit more pure, more along the linear algebra side of things. So first of all, we're going to need to talk about eigenvalues and eigenvectors. Hopefully all of you guys know what they are, but if you don't, then given a matrix, we'll say a n by n matrix, it will have n many eigenvalues lambda, such that this relation holds for a specific vector v corresponding with the eigenvalue called the eigenvector. We're going to denote sigma we're going to let sigma represent the set of eigenvalues lambda of a given matrix. And this is a very useful tool called spectral decomposition, where we represent a matrix A as the product of V times a diagonalization of the spectrum, all of the eigenvalues along the diagonal, and then times V's Hermitian conjugate once again. And V here is the matrix of eigenvectors stacked side by side in the same order as the spectrum, because each eigenvector has a corresponding eigenvalue. Just covering the basics. So we're going to just quickly discuss what an inverse eigenvalue problem is. So talking about a class of matrices C, that this could be Hermitian or positive or symmetric. It could be any type of matrix. We're going to be looking for a set in Rn such that any matrix within the class C, so any symmetric matrix, for instance, will have a spectrum in S. And this is an if and only if relation. So here's another way to put it. So this is the spectrum of M. This is the set of spectra that we're looking for. And if sigma is in S, then a realized matrix such that, well, it's possible to find a realized matrix such that its spectrum is sigma and it resides within the class C. So for instance, here's a matrix that's symmetric. Is its spectrum in S? And also, here's a vector from S. Can we always make a symmetric matrix from it? So that's inverse eigenvalue problem. Now we're going to take a look at graph construction using something called the adjacency matrix. So this is the definition. We'll breeze over that because examples are always nicer to describe things in a talk. So take A to be an adjacency matrix. It's not necessarily always binary, however. We look at the ijth entry as the presence of an edge directed from node I to node J. If the matrix A is symmetric, then I to J has a 1, if J to I has a 1, and therefore it's not directed. But if it's not symmetric, then we call this a digraph where there's arrows. You can't go back along an arrow. So this is how we construct it. For instance, pick the point 0, 0. Looking at all of the diagonals, these would be the reflexive edges that go to themselves. 0, 0 is the only reflexive edge, the only loop here you can see. So here's just a few applications of all of this work, but we'll discuss things later. So circulant matrices are one of the specific kinds of class that we'll be looking at today. They have a lot of really nice properties. So this is a circulant matrix. Given a vector z, we can always make a circulant matrix by taking z to be the first column, cutting the last entry and sticking it onto the top, and continuing this process until we have a square matrix. All of the columns of this matrix would therefore be the ordered cyclic permutations of z. And you can see this diagonal pattern emerging. Using that diagonal pattern, actually, yeah, so here's some graphs of circulants. They're very pretty. They have this rotational symmetry. It's really, really nice. So using this diagonal pattern to the matrix, these are called the permutation matrices, and they are matrices which will take a vector and find a certain permutation of it. And we can express C as a polynomial of this permutation matrix multiplied by each of the values of Z. So Z0 and the identity would place Z0 entries all along the diagonal, for instance. So we're going to quickly have to define the Dft matrix. This is the matrix such that when you multiply a vector on the right-hand side by the Dft matrix, you end up taking the discrete Fourier transform of that vector. And omega here is the root of unity. So it turns out we can find a spectral decomposition of C in this way, using the polynomial of permutation matrices. I'll omit the proof, as I will do for most of this talk, for all of it. And let's just compare this diagonal thing here to what we saw earlier. So from that, it's quite obvious that F bar Z, where bar represents the conjugate, that is the spectrum of any circulant given a sequence Z for the first column. Okay, so moving on, taking this equation, we can then rearrange it using the inverse of the Dft matrix, expressed like this. And this yields this equation. And that's really handy because from that, you can see that any vector in Rn can go to any other vector in Rn from this equation. There's a bijection between Rn and Rn, and therefore this solves the circulant inverse eigenvalue problem for all setting S, the set of spectra, which we can use to be all of Rn. It's universally solved. So now let's move on and look quickly at doubly stochastic matrices. So this is the definition, but I'll put it in slightly simpler terms. It's a non-negative matrix such that all of its columns add up to 1, so they can represent probabilities. And if all of its, sorry, not columns, rows. And if its columns also add up to 1, then it's called right stochastic. And with both left and right stochasticity, it's called doubly stochastic. In other words, if you take the transpose of this matrix, it will still be a stochastic matrix. And remember, with all of these probabilities, we can use this adjacency matrix type stuff to create a weighted graph with probabilities representing how likely you are to move from one state to another on the graph. So the inverse eigenvalue problem for symmetric doubly stochastic matrices, I've said that a lot, so it's just rolls off the tongue now. This has been studied since the 50s and it's still not yet been solved. But today I present some results which solve a subset of this problem, which is quite nice. So here's a few applications. Once again, I don't really want to go over them. They're not really new research or anything. It's just nice to show something real world. So let's solve the SDIEP for circulants specifically. So these are the things that we're going to need. We're going to need it to be circulant, we're going to need it to be symmetric, and we're going to need it to be doubly stochastic. And that has these subcategories to be solved. So let's go through them one by one. So remember how we had this bijection between Rn to Rn? That means that we can always construct a circulant from any vector, any real vector, and we can always any circulant will always have a real vector of eigenvalues, a real spectrum. So that's already kind of solved by assumption. We haven't whittled anything down. We then take the symmetric part of this problem. So something called the Spectral Theorem states that states that the matrix is symmetric if and only if all of its eigenvalues are real. And this holds because the proper theorem involves Hermitian matrices. However, because all of these probabilities have to be real, a Hermitian real matrix is therefore just symmetric matrix. So moving on, we know that all of the eigenvalues just have to be real for that. So we haven't whittled it down yet still, but for constant row sum 1, so that's for all of the row values to add up to 1, we need to look at the Dft matrix. So if you remember, the Dft matrix had the leftmost column being all ones, and this is an eigenvector corresponding with the first eigenvalue called the Perron root. So if we look at this, back at this relationship, we have A multiplied by the vector of all ones times lambda 0, the first eigenvalue, the Perron root, times all of this. If we want row sum to be 1, then A times this will be the vector of row sums. So we want lambda 0 to be 1 for it to add up to all ones. So we need lambda 0 to be 1. That's fixed it a little bit more. So now for real entries, we'll use the following lemma. This is a lemma that I created. There's a short proof, but we'll omit that for time's sake, for brevity. We can apply this lemma to what we had before and let y equal z and x equal to sigma for the lemma. And this means that the elements of z, the sequence, so all elements of the circulant will be real if and only if lambda j is equal to lambda n take j. And that's just this nice symmetry. So that even removes quite a few degrees of freedom on the set from which we can take our eigenvalues. So finally, we just need non-negative entries. And remember, we had a definition of what z is. That is 1 over n times f sigma. And all we need is for z to be greater than or equal to 0. So we just set that greater than or equal to 0 and multiply by n because we have 0 on the other side. So we have this, and it will give us these regions here. And you can keep finding these regions. They're just a set of linear equations, planes, and a nice little interesting feature which I wanted to prove but couldn't quite, is that this region is always an n-dimensional simplex. So it's always some kind of triangle in n dimensions. So either a triangle, tetrahedron, 5-cell, and so on. So we have all of that solved, and that solves the SIAM-IMA for circulant matrices. Finally, we're just going to look at some applications. Using something called Shiga's inequality, we can use lambda 2, in this case, that's the second smallest eigenvalue obtained from the graph G. So a different definition of lambda in this case, lambda 2 in this case. Poor notation, and in combination with phi, which is the conductance of G, we can restrict the conductance of G by choosing specific values of sigma and generating a circulant from that, a stochastic circulant, a doubly stochastic circulant even. So if we want to generate a circulant such that its stationary distribution converges at a desired speed, we choose appropriate spectra from S. So a short description of that is that the conductance describes exactly how quickly a Markov chain will converge to its stationary distribution. That is, how quickly a system will enter a state where its statistical properties don't change anymore. So that's the end of the talk. Thank you for listening. And do you have any questions?
Thank you very much. That was actually very interesting. Not that I was surprised, in case I give the wrong impression, but that was quite interesting, actually.
Thank you.
Do we have any questions from our audience? Well, while
don't worry, no one else got any questions.
well, you should expect one from me. Can you perhaps elaborate a little bit on the Markov chain part? I mean,
yes,
I know what you mean about the right. Okay.
Yeah. So as I was talking through this, I was thinking, oh no, none of you know what Markov chain is. Well, not necessarily all of you. I mean, so maybe I could take it back to. Oh no, that's full screen. What has happened? Yeah. Okay, let's go back up to this point. So a Markov chain is, imagine placing weights on all of these arrows and their probabilities. So their likelihoods that you're going to go from a state 2, for instance, to a state 1. And the sum of all of the probabilities, all of the weights coming out of a node has to add up to 1, because that's all of the, it's the likelihood that something happens, but which always happens. So how do I say this? So when we have our circulant with different values in all of these positions, all of the values have to add up to 1 in the same way that all of the values around traveling outwards from a node have to add up to 1. So you could think of that perhaps as different states of a poker game. So the likelihood that given 3 cards have been placed down, you know that state could go to another state. So let's say this is, you currently have 2 pair. No, yeah, 2 pair. What's the likelihood that you go to full house? If you play poker, or you could think of it as weather instead. So the likelihood that, given that you were on a sunny day, what's the likelihood that tomorrow is going to be raining? Yeah, so that's a Markov chain.
Thank you. So I guess, okay, so perhaps you should have asked the question a bit better, but now it's useful because you have introduced the concept. How, okay, so if you have a graph or if you have a system with states, then you can associate a Markov chain with it. And I mean, you start with some probability distribution, which, for example, could be, I don't know, weights between the nodes, right? And then you're looking, basically what you were saying at the end of your talk is basically you're looking at the stationary distribution.
Yeah.
So you need some properties for convergence and things like this, right? How is this related to your matrices? This is my question.
Right. Okay. So, well, it's the stationary distribution of a random walk going on for an infinite amount of time. So it's the likelihood that your random walker will be in a given state after a large amount of time. So there's a lot of like ergodicity involved. So you could think if you give it maybe 10 steps, then the likelihood that you find a random walker at a certain location will change on the next step. However, if you leave them running around on this finite graph, it's guaranteed to converge to a stationary distribution. In other words, you're guaranteed to end up with very fixed probabilities, no matter, so very fixed probabilities. So if you were to wait an unknown amount of time and guess, oh, what's the weather going to be like now, then that probability is stationary. It's converged to that probability. Does that make a bit more sense?
Mm-hmm.
So the speed at which it converges to that, so this random walker is walking around, and it's constantly shifting the likelihood. So maybe after five steps, it might be so likely to be at 1, 2, 0, 3, 4. Those probabilities will be ever changing as the random walk goes along,
Right.
but they will get closer and closer to a stationary distribution.
So it's a convergence of distributions basically here.
Yes.
So you started with the distribution and then, so I guess what I'm curious about is whether this is, how is it connected to your stochastic matrices? Like, where is the Markov chain coming in? Which
with the circulates or with the inverse eigenvalue problem? So if you can choose the eigenvalues, if you know which eigenvalues to choose, such that you can always make a doubly stochastic matrix.
Right.
And in fact, with this, we have a method to realize them. We have a method to construct one such that its spectrum matches a prescribed vector.
Okay.
Then you can choose for the second smallest eigenvalue, which I think is called the Dirichlet value or something like that. You can choose this, you can fix it and say, I want this to provide really strong tight bounds on the conductance of G. So we want it to converge really, really quickly. And so you can construct Markov chains randomly with a which will always converge quickly.
Okay.
Does that make sense?
Yeah.
You could have create
right.
a program that will always spit out Markov chains which converge very quickly.
Oh, okay, I get it. Okay, thank you very much. That was very interesting.
Thank you.
So another question from Ian. What software do you use or code do you use for your work? I suspect for the simulations, perhaps. I mean, this is mostly theoretical, right?
Yes, it's mostly theoretical. However, I did do some statistics and I used NetworkX on Python.
NetworkX, okay.
Yeah, but it's a little bit fiddly to use. Well, I use NetworkX to represent the graphs and to do all of that, but really you can just use NumPy.
Okay.
Or just linalg, all of those Python things. Is it the Markov chain that makes it stochastic? No, so a Markov chain is a representation of how a model changes, different states, different likelihoods of going from a state to another, and you can turn and yeah, so the randomness of that, I guess, makes it stochastic.